Alrighty, here we go. This should match the notes sheet that you should find through our Google Calendar, kind of like the agenda for every day. We're going to start with an introduction to limits. So the first unit is called limits, and it's of course going to be new notation and new vocabulary for a lot of it. Starting with this first idea about what a limit is. So a limit is the y value that a function approaches at a given x value. Okay, so the answer to a limit is a y value, always and forever. Okay, the other thing to kind of keep in mind here is that we're talking about what the function is approaching. It's not always what the function's y value is, but sometimes we count what it's approaching as its limit. So let's look at a very basic example here. First one. So over here we have a limit. And of course I wrote on it, so it's kind of hard to see. But there is like a little black arrow here between the x and the 2. I'm trying to emphasize that there. So the way we read this problem is we say, find the limit as x approaches 2 of the function 2x minus 1. So we've got two ways to do that. So the first way is the easiest way, and this will work for all functions if you can get it to work, is by plugging in the x value. So we put in the x value of 2 into the actual function in the notation, and we work out that math. 2 times 2 minus 1 ends up being 3. Okay. The second way to do it is over here if you look at a graph. So the limit as x approaches 2, so I want you to know x approaches 2. This is the x value that we're honed in on, of course. That pairs with the y value, right, that the function is on at that moment. So the y value is 3. There's really no question about it. And that's our limit. It is 3 for the same reason as way number 1. Okay, both graphically and what we call algebraically, you should get this limit to equal 3. Okay. Now, aside from regular limits, we have what we call one-sided limits here. So the first thing is a left-hand limit, and that is written this way with the little minus sign after the x value. The way we read this is to say the limit as x approaches c from the left of f of x. Okay, it doesn't mean anything to you yet until we look at a graph, but that's how you would say that question. Okay, the other one is a right-hand limit, and that is the limit as x approaches c from the right of f of x, right? We just have a little plus sign after the c to indicate the right side of the x value. And that's really all the minus and the plus sign mean. Now we have to figure out how to use them. So we're going to look down here at this example with these questions down below. So we're going to start off with questions 1, 2, and 3 at the bottom. And this crazy graph, you see I have some arrowheads on here. It'd be nice if all those colorful arrowheads were off, but I'll explain what each of those mean in a second. So question number 1, this is a graphical limit we're going to find. It says to find the limit as x approaches -4 of f of x, right? So our eye is drawn to -4 on the x, axis, and then we look up to what the y value is. Okay, y value ends up being 2, so boom, our limit is 2. We go over to question 2, and this is where we bring in this one-sided idea. So now question 2 says, what is the limit as x approaches 2 from the left with the little minus sign? So we are going to kind of switch our thinking here and to think about being on the left side of 2. So here's 2, right, on the x side of things, and then we're going to approach it from the left-hand side. So we are going to start on this side of the function and work towards the x value of 2. And whatever y value we get to at this point, right, we get to y equals 0. Okay, we're going to put 0 down below. The next question is kind of the opposite side of things. The next question, number 3, says, what is, as x approaches 2 from the right-hand side, what is that limit? So that would be taking your thinking and your pencil or whatever to the other side of the function. So we're going to start on this side and head towards 2. Okay, and we also get to that y value of 0 at that point. See how the green and the blue come together to touch? That means that they should have the exact same limiting value, okay, of 0. All right. All right. Let's keep going here. I got a couple more examples down below. Let's do 4, 5, and 6. So question number 4 is asking the limit as x approaches 3 from the left of f of x. So again, we zero in on the y value of 3, or nope, the x value of 3, and then we are going to be on the left side of it with our thinking. So that means this side of the function approaching that hole. Okay, that's an actual hole in the graph. So this is where the definition of the limit comes in handy, because we're not saying what is the function's value, right? Since there's a hole there, the value is not 2. But the actual, y value of that hole, right, is 2. So we say that that is the limit. Okay. So if we look at the next part, the next part says to find the limit as x approaches 3 from the right-hand side. So we're going to take 3 from the right-hand side. That means we're going to be on this side of 3, and we're going to move towards 3 itself. And again, we come to the same hole. We come to the same y value of 2. So we report down below that our y value is 2. Okay, or our limit. Okay. Number 6 is kind of a combination of questions 4 and 5. 6 is a different question. It's asking what is the overall limit as x approaches 3 of f of x. So you notice there's no plus or minus to indicate it's the left or right hand limit. Since number 4 was 2 and number 5 was 2, I'm going to get number 6 is also going to have to be 2. If those two limits match, the left and the right hand side, the overall limit is always going to be the exact same value. Okay. Number 7 and 8, sorry, let's try to zoom a little bit better here. 7 is asking about x approaching -1 from the left of this graph. So -1 from the left is a lot to wrap our mind around. So -1 is here on the x-axis. The left-hand side of it, right, is, let's try to keep colors the same here, over here. Okay, and I am approaching a hole again, but that hole is situated at the y value of 3, right? So I'm going to report 3 as my limit. In number 8, I'm going to be on the other side of -1. Okay, with the little plus sign, that means I'm approaching it from the right-hand side. So I'm going to get on the right-hand side of -1, and I'm going to follow towards -1. And it looks like the y value at that point is 1. Okay, so again, here's that y value. It's approaching 1. Okay, so we put 1 down here. For the first time, for number 9, you notice if we ask you the overall limit at -1, we have to say DNE for does not exist. Right? Straight up from Mean Girls. This is where it comes from. So the limit does not exist there, because if you kind of look at the graph up above and look at the highlighted regions, at -1, the blue highlight and the green highlight do not come together. So the limit doesn't exist. That other one that is still highlighted, right? Those two little highlighted regions do come together. So the limit does exist, and it's at 2. Okay, this leads us to kind of our first theorem here. So it's the existence of a limit at the top of the page. Limit as x approaches c of f of x exists if the limit on the left-hand side is equal to the limit on the right-hand side. So that's what guarantees a limit existing. When the left and right-hand limits are the same, we for sure know that the limit exists. If the left-hand limits and right-hand limits are not the same, we're not sure if the limit's going to exist. Okay. Example 2 here is a little bit, it's the function itself is a little obscure, but we actually use this function and translations of it a lot in calculus. So you have to think for a little bit of time about like plugging in x values to absolute value of x over x, and then figuring out what their y values are in order to get the graph. Okay, so the graph is there in the kind of like, it kind of looks like maroon on our screen. So again, the orange and the blue arrowhead are from when I was kind of writing on these paper notes before. So kind of try to ignore those while we think about it. So if you plug in -2 to the function, you're going to get the absolute value of -2 divided by -2 itself. So the top, of course, becomes +2. The bottom is still -2. We divide that out, we get -1, right? And so we're just plotting that point right here. right? If we plug in -1, we get the exact same output. And if we plug in 0, it actually doesn't exist. And this one is the weirdest function in the world. It's going to be a hole right there. Okay, and then this branches off this way. Okay, on the right-hand side of 0, if you plug in 1, right, the absolute value, so basically the numerator and the denominator are going to be the exact same. So when you divide it out, you're going to get 1. And if you plug in 2, you're basically doing 2 divided by 2, which is 1. Plug in 3, 3 divided by 3 is 1. And then that's how we get the top branch of this function. Okay, we usually translate it left and right throughout the course. So it's a really good one to kind of get to know, obviously, right from the beginning. So when we look at these limits then, after we compile a graph of the function, if we try to do limit question number 1, find the limit as x approaches 0. I think that's on the right. It's kind of, it didn't scan well, but it's on the right-hand side of 0. So we're going to again think the right-hand side of 0 is over here, and we're approaching this way. So the y value there is 1. In question 2, it says x approaching 0 from the left. Okay, so again, we kind of eyeball 0 on the x-axis, and then we approach it on the function, and it looks like that y value, of course, is -1. Okay, again, because parts 1 and 2 are not the same number, for question 3, when it asks for the overall limit, we get to say does not exist, because those highlighted regions do not come together at the same y value. Individual one-sided limits do exist, but the overall limit does not. Okay, and then lastly, number 3 down here, quick review of rational functions. It says to graph f of x equals x squared minus 1 over x plus 1, and find the limits, of course. So we're going to start off, any rational function we get, we're going to factor it right away. So I factor the top using the difference of squares up here, right? X minus 1 times x plus 1, and then the bottom is still x plus 1, and those cancel out. So I can use that information here, right, to go ahead and find the whole. So if I take the factor that cancels and I set that equal to 0, I get x equals -1. That is the x value of the whole. And then if I take that -1 and plug it into what does not cancel out, right, all this stuff, when I plug -1 in there, which is this notation here, I get a y value of -2. So that's how I know where to put the whole on the graph. So you can see it very visibly in the graph itself. And then, of course, the rest of the graph is going to look like y equals x minus 1, right, over here, because that's the part of this rational function that did not cancel out. So basically, it's just a line, right, with a hole in it. So when we do part 1, it asks for the limit as x approaches -1 from the right. Again, the scan didn't copy so well. So -1 from the right is what that little plus sign I was trying to draw in would be this. -1 from the right. I'm approaching -2. And then question 2 says x approaching -1 from the left. So now I'm going to be on this side of things, heading towards -1 on the left-hand side. I get to the same y value, -2. And since those two highlighted regions come together, I'm going to put my overall limit in part 3 as -2 also. Okay. There's a couple summary questions for you to do down here below. So I want you to take the time to fill those in. There's no right answer. Some of you will write different things, and that's okay. And then we'll just be ready with this information for the next time I see you. Okay, great job.